Yeah, so I'd like to thank Philip for like excellent introduction. So my job is like really much easier right now. I can only tell you half of the presentation, the other half is covered. So we can have happy hour. So, let's see, no, I cannot. I have to do it, but okay, it's okay. So this stuff you already heard. So I will not go through this. I only will mention why is anatomy important. So anatomy is important because if you want to think of an immune-mediated disease like lupus nephritis, then the immune cells clearly coming from the blood, right? So it helps to get a sense, you know, where do the cells go first and where second. And the only thing that I think is interesting to highlight here, because I mean Philip did make like an excellent job of saying interstitial inflammation is important also for the glomerulus. And what's really perplexing here is that if you look, well, let's see, from here, if you look, so the blood comes in here, right? And then it flows down this artery, and the glomeruli up here at the cortex, so it's like all around the rim of the kidney. So the blood comes in here and has to pass through the glomerulus before it exits the glomerulus to go to the interstitium. So when we talk about interstitial inflammation, all the cells have gone through the glomerulus. So I mean, this is something like really complicated because everything has seen the glomerulus first before going to make whatever interstitial inflammation you want to make. And we don't know why that has to be this way. So this is something that's interesting. I mean, people are investigating stuff on this direction. So that was mentioned already, but it's exactly what I said. You go in the glomerulus, you exit the glomerulus, and then you, especially then as you exit the glomerulus here, you will go and give blood to the interstitium. Already Philip mentioned, so I won't go through this again. What is kidney disease? I mean, and especially in this case, what is glomerulonephritis, so a glomerular-like targeted disease? The thing that we're interested in is to lose this filtration possibility. And so from my point of view, I will only mention the cells that are like taking part on this filtration, and this is the endothelial cells. And on the other, so endothelial cells on the vessel side, and those are really cuffed by another cell type, which is like really interesting. And those are the podocytes. So the podocytes, as they sit on this basement membrane and hug it, they make a synapse, which has many proteins that you also find in a neurologic synapse. So it's like a highly specialized structure there. What happens in lupus nephritis essentially is that those food processes here are getting effaced, and as we said, that's not the only part, because that's the first thing, proteinuria, and then the second would be kidney inflammation. So I won't go through this again, so a normal glomerulus, and now let's go to lupus nephritis. So in this case, so blood comes in here, urine gets in here, and then blood will exit from the glomerulus if it doesn't, like whatever is not filtered in the urine. And this is now mouse, but it's a good mouse model. So these are the NZBW mice. Many people use them as a model for lupus nephritis because they mimic many of the things that happen in humans with lupus nephritis. And what we see typically with the NZBW mice is that as they get older, the glomerulus looks like this. So this is the same magnification in these two pictures. And the difference is, like, you can see the glomerulus is enlarged, and that's because it has more cells there, immune cells, but also the mesangial cells that are in the glomerulus proliferate, and there is more like matrix deposition, so the architecture of the glomerulus has now changed. And that happens just with age. And this is like how the electron microscopy looks. So this is a normal filtration, so this is the blood side. So from the endothelium you go through this basement membrane towards the podocyte food processes, and this is a nice podocyte which makes all these processes. And here's the urinary space. And in the case of nephritis, the food processes are effaced. So essentially you have no food processes, the filtration doesn't work. And what is specific for lupus? Because I mean, losing your podocytes and losing the food processes is like a common downstream thing in many glomerular diseases, in all glomerular diseases. So what is special for lupus, and we don't know why it is that this is what happens this way, but what is special for lupus is that you have, as Philip already mentioned, you have loss of tolerance against nucleic acids. So in all lupus patients, we find in the blood anti-dsDNA antibodies. And why would loss of tolerance to nucleic acids lead to nephritis? And is that important for nephritis? I mean, it's also that in all lupus patients we find these deposits in the glomeruli. Are those important for glomerular disease? I mean, in the end of the day, we don't know. I mean, people have looked a lot. I mean, there's no really single paper that would tell you that deposits alone is what makes disease, right? It's just that we always see them. So that's what we tell, actually, because I also have been in the clinic, so that's what we tell students in the clinic. If there's no immune complex deposition, this is not lupus nephritis. Same with the mice. If there's no immune complex deposition, this is not lupus nephritis. That said, we don't know the deposits is what causes the nephritis. So this is now where it gets interesting for the macrophage side. As I said, we don't know that the deposits alone are enough to get severe nephritis. And this is a paper from Jeff Ravage's group from Rockefeller in the 98, where he just showed exactly that. So what he did, he took this painful model, the NZBW mice, which have many polygenic genes that cause nephritis. So it's not just one gene, it's many genes. And therefore you cannot just cross to some knockout. You have to do it for a decade. So he crossed the NZBW mice into mice where there was no gamma chain in the Fc receptors. Now, Fc receptors are receptors that are on phagocytes and recognize immune complexes. So the gamma chain is like an activating protein in the Fc receptor complex. So if you don't have the gamma chain, there will be no activation of the cell having the Fc receptor. So that cell will not be activated by immune complexes. And what he showed here is that BW stands for NZBW mice. So this would be like take your control, like it will lack one of the two gamma chains. So this mouse would get nephritis. But if you had no gamma chain, nephritis kind of still happened. So you still had deposits, but it was very mild. So when he measured podocyte injury, that is proteinuria, it was not there. And what is interesting here is that when he measures autoantibodies or loss of tolerance in the blood, he still had loss of tolerance. So here we have a situation where you have anti-dsDNA antibodies. You actually also have deposition, I'm not showing you, but nephritis is mild. So that's what he called uncoupling of immune complex formation with kidney disease. That's what Philip was mentioning. You actually need a kidney component, a kidney inflammation component downstream of loss of tolerance to get kidney disease. So this was interesting to us. So we wanted to actually understand a few of the pathways that determine the severity of kidney disease. Once you have lost tolerance, because if you don't start from loss of tolerance to nucleic acids, as I said, this is not lupus nephritis, at least by definition. So there's a ton of papers. There are 15 papers in the literature in the last 10, 20 years, and they keep enlarging, where they show that type 1 interferons are important in mediating disease. And that's, to most of people here, I would guess obvious, because, when you have something that's caused by nucleic acids, like a viral infection, you activate type 1 interferons. So same in lupus, you activate type 1 interferons. And type 1 interferons are sort of an immune stimulant. So everybody who has tried to block type 1 interferons in the mice, like in different ways, or supply type 1 interferons, got the worst type of disease. So blocking better disease, supplying worse disease. And so that was known. What was not understood so well is what do type 1 interferons do in the kidney. So what we did here is that we gave either poly-IC. Poly-IC is a synthetic double-stranded RNA that induces type 1 interferons in the blood, or we gave to the mice an adenovirus expressing type 1 interferons, so either or. We had the same phenotype in both cases. And the phenotype was that you got, this is not very easy to appreciate here, I'm sorry. You have this type of glomerular disease. So the difference between this glomerulus and this glomerulus is that you have this thing around the glomerulus, which is like a layer of cells. Actually, it's 2 or 3 layers of cells. And this is called a crescent, like in German, Halbmondbildung. So essentially, you have proliferation of epithelial cells that surround the glomerulus. And that in humans is a type of aggressive disease, so it's called crescentic nephritis, and when the pathologist sees that, knows that the patient has a worse prognosis. So giving interferon to the mice caused crescentic nephritis. What we saw there is that what many people have observed now in other types of crescentic nephritis is that the cell that responded the most in this case, the cell that was activated the most by type 1 interferons, was the macrophages. So this is what's shown here. So by CD11B and GR1 would be for neutrophils like GR1 high are neutrophils. So here's where you expect neutrophils, and there are few, but compared to the macrophages, very few. So you have quite a lot of macrophages there, and F80 high are like the kidney macrophages. So basically, this is when you have both polyasci and disease, kidney disease, proteinuria. And what about other immune cells? I think T cells are still important in this model. Like what happened when you gave polyasci? So you do have T cells. These are these here. You have very few B cells and very few neutrophils. Here, a disclaimer: there is no plasma cells in there because this stain was done with B220. The plasma cells often would not express B220. So now we know there's also an increase in plasma cells in the kidney in this case. So T cells are certainly there. I don't want to make people think that this is not a T cell mediated disease, and I'll show you later why. But macrophages proliferate like crazy when you give type 1 interferons. And that you can see here. So this is a glomerulus in the middle, and you have CD11B positive cells like surrounding the glomerulus. And we have a stain for F80 later. So are macrophages important? We heard they are. Yes, they are. I mean, when you take when you give like a general treatment, clodoronate, which gets eaten up by phagocytes and causes apoptosis, then the crescents are gone. And people have seen this also in other crescentic glomerulonephritis that are not lupus nephritis. When you take the macrophages away, crescents are gone. And we wanted to understand a bit why. So these are the effects that happen when you take the macrophages out. So the one thing, deposits are not gone. Deposits still there. Same as I showed you with the FC receptor gamma chain knockout, deposits were still there, just disease is not severe. The second thing, we took like in situ zymography. That's a quite easy assay. It sounds like complicated, but it's easy. So you just take an unfixed kidney section and you incubate with DQ gelatin. So basically, if you have activated metalloproteinases, which cause tissue remodeling in the glomerulus, then they will eat up the DQ gelatin and it will all become green. So when you do that assay with like, when you have given polyasci, you have this really green stain of the glomerulus, and when you have the macrophages out, it's weaker. So basically, this shows you that tissue remodeling, like eating up the tissue within the glomerulus in the absence of macrophages, is way better. So the other thing that happened when you took out macrophages, because I told you type 1 interferons are important, so we measured type 1 interferon responsive genes in the kidney. And those, interestingly enough, they don't go up early, they go up only when you have proteinuria. So when you give polyasci, you have an increase here in ISG15 and STAT1. And when you take the macrophages out, although the mice still had proteinuria, there was no type 1 interferon responsive genes detectable. So that seems like a general like inflammation response, like lupus-specific inflammation response that's improved. And so we isolate the macrophages, and I think this is the one important piece from this older story. So people think of macrophages as pro-inflammatory, so they would secrete, let's say, TNF, and actually TNF is known to be increased even in this model, in lupus nephritis, but the macrophages don't express TNF. So I think that's also important because more recent work has shown that when you stimulate kidney macrophages with immune complexes, they produce TNF. In this case, no. So to our surprise, we saw that the macrophages were expressing tons of IL-10. And what was important in the end is that they expressed this molecule, many people have followed on this, which is called HBGF. It's a trophic growth factor. It signals on other cells that have an EGF receptor to proliferate, and actually proliferative lesions. So that was important. This is also for the whole kidney. If you took the macrophage out, there was no HBGF expression, or PDGF, another trophic, or TGF-beta, very important. So people have followed up on this through the years. And the one paper came out, like this was not specific for lupus nephritis, but they showed that presentic nephritis depends on EGF receptor signaling, so you need trophic signals for epithelial cell proliferation. And then the other paper just came out that shows it in lupus nephritis model that actually also there you need the EGF receptor signaling for crescent formation, and they also show that you need TNF for the EGF receptor signaling to be activated, though we still don't know who makes the TNF. And actually this project was done in a big part by Tom Ashman and Jason Vignaris, and they've done great work. So yeah, so thanks to everybody for holding on.